Chapter 25, Vibrations and Waves. All around us we see things that wiggle and jiggle. Even things too small to see, such as atoms, are constantly wiggling and jiggling. A wiggle in time is a vibration. A vibration cannot exist in one instant, but needs to move back and forth. Strike a bell and the vibration will continue for some time before they die down. A wiggle in space and time is a wave. A wave cannot exist in one place, but must extend from one place to another. Waves travel. Light and sound are both forms of energy that move through space as waves. This chapter is about vibrations and waves, and the following chapters continue with the study of sound and light. 25.1 Vibrations of a pendulum. Suspend a stone at the end of a string and you have a simple pendulum. Pendulums swing back and forth with such regularity that they have long been used to control the motion of clocks. Galileo discovered that the time a pendulum takes to swing back and forth through small angles does not depend on the mass of the pendulum or on the distance through which it swings. The time of back and forth swing, called the period, depends only on the length of the pendulum and the acceleration of gravity. Over here we see figure 25.1. Two pendulums of the same length have the exact same period regardless of mass and also regardless of the angle that they're released from. A long pendulum has a longer period than a shorter pendulum. That is, it swings back and forth more slowly, less frequently than a short pendulum. When walking, we allow our legs to swing with the help of gravity, like a pendulum. In the same way that a long pendulum has a greater period, a person with long legs tends to walk with a slower stride than a person with short legs. This is most noticeable in long-legged animals such as giraffes, horses, and ostriches, which run with a slower gait than do shorter-legged animals such as dachshunds, hamsters, and mice. Section 25.2 Wave Description. The back and forth vibratory motion, often called oscillatory motion, of a swinging pendulum is called simple harmonic motion. The pendulum bob filled with sand in the figure exhibits simple harmonic motion above a conveyor belt. When the conveyor belt is stationary, the sand traces out a straight line. More interestingly, when the conveyor belt is moving at a constant speed, on the right-hand picture, the sand traces out a special curve known as a sine curve. Figure 25.2. Frank Oppenheimer, founder of the Exploratorium Museum in San Francisco, demonstrates that a pendulum swinging back and forth traces out a straight line over a stationary surface and a sine curve when the surface moves at a constant speed. The same can be done with a weight attached to a spring undergoing vertical simple harmonic motion, shown in figure 25.3. A marking pen attached to the bob traces a sine curve on a sheet of paper that is moving horizontally at constant speed. A sine curve is a pictorial representation of a wave. Like a water wave, the high points are called crests and the low points are called troughs. The straight dashed line represents the home position or midpoint of the vibration. The term amplitude refers to the distance from the midpoint to the crest or trough of the wave. So the amplitude equals the maximum displacement from equilibrium. Basically, the amplitude is how big the vibration is. The wavelength of a wave is the distance from the top of one crest to the top of the next one. Or, equivalently, the wavelength is the distance between successive identical parts on the wave. The wavelengths of waves at the beach are measured in meters, the wavelength of ripples in a pond in centimeters, and the wavelength of light in billionths of a meter, nanometers. How often a vibration occurs is described by its frequency. The frequency of a vibrating pendulum or object on a spring specifies the number of back and forth vibration it makes in a given time, usually 1 second. A complete back and forth vibration is 1 cycle. If it occurs in 1 second, the frequency is 1 vibration per second or 1 cycle per second. If 2 vibrations occur in 1 second, the frequency is 2 vibrations or 2 cycles per second. The unit of frequency is called the hertz, Hz. A frequency of 1 cycle per second is 1 hertz. 2 cycles per second is 2 hertz, and so on. Higher frequencies are measured in kilohertz, kHz, which is thousands of hertz, and still higher frequencies in megahertz, MHz, millions of hertz, or gigahertz, GHz, billions of hertz. AM radio waves are broadcast in kilohertz, FM radio waves are broadcast in megahertz. Radar and microwave ovens operate at gigahertz. A station at 960 kilohertz on the AM radio dial, for example, broadcasts radio waves that have a frequency of 960,000 vibrations per second. A station at 101 megahertz on the FM dial broadcasts radio waves with a frequency of 101 million hertz. A mega is a million. These radio wave frequencies are the frequencies at which electrons are forced to vibrate in the antenna of the radio station's transmitting tower. The source of all waves is something that vibrates. The frequency of the vibrating source and the frequency of the wave it produces are the same. If the frequency of a vibrating object is known, its period can be calculated, and vice versa. Suppose, for example, that a pendulum makes 2 vibrations in 1 second. Its frequency is 2 hertz, 2 vibrations per second. The time needed to complete 1 vibration, that is, the period of vibration, is half a second. Or if the vibration period is 3 hertz, then the period is 1/3 of a second. As you can see below, frequency and period are inverses of each other. Frequency equals 1 divided by the period, and vice versa. Period equals 1 divided by the frequency. Questions. What is the frequency in vibrations per second of a 100 hertz wave? Answer, 100 vibrations per second. Number 2. The Sears building in Chicago sways back and forth at a frequency of about 0.1 hertz. What is its period? Answer, its period is equal to 1 divided by the frequency. The frequency is 0.1. 1 divided by 0.1 is equal to 10. So the period is equal to 10 seconds.